And this you can actually run on Jupyter
This
Notebooks.
meeting is being recorded.
Oh. So you can run on Jupyter Notebooks, and that's basically another way for you to learn, is going through this tutorial on your own and then trying to change things and see how things behave. Here we are showing, when you show it on Matplotlib, but if you can have KLayout open, you will be able to also see it directly on KLayout. And this works thanks to another GDSfactory extension that we made, where it's basically running a TCP server on KLayout, waiting for GDS files to be streamed from your it's basically an HTTP. So you basically HTTP send the GDS, and magically will show here. Before we had this available, you have to go file, open, and open the GDS every time you would make a change. But this integration makes it almost like, we call it KLayout Live. So the KLayout macro will allow you to refresh the GDS interactively. We have another mode where you can run a file watcher. I can show you this later too. So you can run a file watcher, and then you can define your circuit in YAML or in Python. I usually use them in Python, but there's also the people who define their circuits and mask in YAML. And then with the file watcher, you don't even need to run the file. As long as you save it. Once you save it, it will detect there's a change, and it will refresh. This makes your GDS instantaneous, because you will see that GDSfactory has a cache, and basically the cache will make the rebuilding the circuit very fast. We also have simulation plugins. So this is one of the simulation plugins. It's a mode solver that allows you to compute electromagnetic modes that are supported by different waveguide cross sections. So we added recently an FEM measure, so you actually can take from layout and create like a mesh. This is useful for TCAD and thermal simulations. We have a heat solver also, a finite element method. You can see how as you have a heater on top of your waveguide, there's a time constant on the heater where the heat takes some time to propagate all the way to the waveguide. So you can calculate what's your RC, your bandwidth of your heater. You can also operate it in reverse, where you actually see the cooling. We can also do TCAD simulations, where you can actually simulate how a doping profile, basically, once you have an doping profile and then you apply some voltage, you will simulate drift diffusion equations with a Poisson solver. So you can see how the junction is going to change over voltage. So these are all, so far what I've talked, is all open source. You don't need any licenses. You can even see the code yourself, and you can even make improvements. So whenever when you're doing some research, which is usually making something that nobody has done before, like having access to open source tools can unlock you and basically enable you to do innovation. You don't depend on a vendor to do it for you, and you understand all the physics on everything that's going underneath. For finite difference time domain, this is a very common way to simulate the S parameters. So the S parameters is basically the relationship of the output fields versus the input fields for different electromagnetic modes. So here we're doing it from the fundamental TE mode. So you can see the modes of the inputs and the outputs, and then you can see how this 3 dB splitter splits the light evenly, 3 dB. We added recently also topology optimization, where you can actually do inverse design directly from GDSfactory, thanks to the MIP adjoint optimization techniques. Something we also been doing, so we've been doing optimization using Google Cloud Platform. So there's some notebooks here. You can see I have the link underneath. So basically, this is a black box optimizer. When you want to optimize this, this is a 3 dB splitter. So light comes in from the left and divides 50% power on both arms. So for depending on the platform, this is, for example, silicon nitride. You need to compute the width and the length. You can add more parameters later on, like what's the gap between the waveguides, what's the taper length. But the most important ones are the width and the length. And you can see how the optimizer tries to sweep the whole parameter space, trying to find what's a good transmission. So in the end, you want 50% transmission, 0.5 on every port. So you can see it finds good numbers around here and tries to fine tune it more. So starting with a width of 3 and a length of 13, with a 2% transmission. The optimizer converges after like 167 trials to 49.7% power on every arm. Another thing we added recently is a circuit simulation when you have layout aware of Monte Carlo. So this is basically taking the FDD parameters that we've done before with an S-parameter solver such as MIP or Tidy3D or numerical FDD. You can take that and put it into a circuit. And this is basically a linear circuit solver. It's very similar to when you do the T matrix, but this is S matrix. So you can actually account for any reflections and any it's a linear circuit solver that you compute. And if you basically try to model like width and height variations that you get on a real wall fabrication environment. So once you project this into a wafer model, like this is a randomized wafer topography model where you have width and height variations, you can see that the top layout behaves much worse in terms of variability. So you can see the nominal is this line in red, and the variability of the Monte Carlo simulation, it gives you an RMS of 0.17. But if you do the layout a bit different, where both arms are folded on the same direction, you can see that the RMS goes from 17 to 7. So it's a big reduction on the variability of your circuit. And these are kind of things that you can start modeling now thanks to the layout aware Monte Carlo with stacks. And yeah, and the last part I want to cover, the second part is the verification. So we've covered the design phase. We will go through verification, and we will be playing with this. I made some exercises that we can go through together. But if anyone has questions, you can ask now or later during the workshop session. The DRC part is basically, we have two types. So we have connectivity checks, and then we also have DRC. You can see all these, everything I'm explaining here can be accessed from the GDSfactory website. You can see here, basically what I did is just see the slides. And these are the slides I'm presenting. So you can also watch this later. You can also watch some YouTube videos where I start to break some of the contents into small 10-minute videos. And then this is the documentation that we are seeing. So as you can see, we have different plugins. So the layout tutorial is the one that we're going to start today, because layout is usually the first step that you need to do before making a chip. Then you need to make sure you optimize it and simulate it. But yeah, like you can see that we support different mode solvers. We support 2. We support like 3 FTDD plugins. FTDD, MIP, and numerical. FTDD, MIP, and numerical. Like Tidy3D, MIP, and numerical. And then we support also 3 circuit simulations frameworks. So the idea is that it's a foundry agnostic, tool agnostic. It is a Python API that try to drive different tools with a common interface. And that's one of the limitations of open source tools. Like, they all have different APIs, Python library interfaces. So here what we're trying to do is we're trying to do a write parameter code that is as similar as possible. You can see on the API. So if you go to the FTD simulations, the write parameters MIP is very similar to the write S parameters on Tidy3D or write S parameters for numerical. It's just a common API to basically drive different tools without you having to learn 3 different tools to do the same task. So this allows you to easily benchmark different tools and choose the tool that you need for your needs. Without having to remake your code, try to learn a new API. And in most cases, we even give you an alternative that I'm mostly using basically I'm using all open source tools in my design. So that this allows me to, as I showed before, I can do like parameter exploration with 100 of machines running at the same time. And yeah, so we were covering the DRC verification. So you can see you can do connectivity checks, you can do DRC. And the DRC, you can also read about it it's not part of the layout tutorial, it's part of the installation, like K-layout integration. Because in the end, it's a K-layout way to write GDS. So you can see how easy it is to refine your rule deck. It's basically a minimum width, minimum space. And these rules of minimum width and minimum space allow you, when you send this chip to the factory, they will assure you that if you respect this value, the chip will be fabricated correctly. So you have to make sure they pass this. So yeah, I've been trying to also work with the foundries to be able to support GDSfactory and K-layout as a way to run DRC and other checks. And the last part I'm going to cover is after you get your chip back from the fabrication is the validation. So the validation is basically, we have some data analysis scripts, and then we have also a database. It's an open source database schema that you can use to store your simulations and be able to query them from the database. And yeah, as I said before, we're supporting multiple GDSfactory PDKs. You can ask your foundry for the PDK. And yeah, we have this available. I've been also trying to work with some open source developers at Google who also have been working on CMOS PDKs. So these are CMOS PDKs, they're not photonics PDKs, but we've been supporting them. And there's some people using this tool for analog design, which was not supposed to, but people are using it now because we have auto route on placers. So you can see one of the chips that was made by University of Michigan using GDSfactory. So this is a CMOS chip. And yeah, finally, there's a lot of people here. Yeah, some of them are in the room, and hopefully we get more people involved as well and contributing. But yeah, you can just start using it, and if you find some improvements, any component you read from a paper or anything you find useful, you can always contribute it back. So how do we get started? So you can actually learn from the browser. So you can run all these notebooks I'm going to show from the browser. The thing is, the browser, this binder thing, it will time out after like 10 minutes. So you need to connect to Git and be able to store your work. So what we're going to try to do, we're going to try to install it on your computer, which is a bit of a risky task, but because there's more people in the room, that you guys can help each other. So you will install it on your computer. The first thing you need to do is install K-layout, which is the layout viewer. Then we're going to install the latest GDSfactory release, and then we're going to try to do some exercises. So I put together some small exercises that we can do together, and people can see. I don't know if it's big enough. Maybe I can fit it. So yeah. So the first thing we're going to do is we're going to install the K-layout layout viewer, and we're going to install the latest GDSfactory. And then once you have K-layout, you will install the K-layout integration. The layer integration is basically, if you go to Tools, Manage Packages, you will be able to see, I mean, I already have the two packages installed that I'm going to use for the demo. And one of them is the GDSfactory tool, and the other one is the K-layout pixels. This is basically so you can see the cross-section of your chip. So we can do that together, or you guys can start, and then I can start also with the first exercise of like doing a Mach Zehnder interferometer. Yeah, like by default, if you are on Windows, it will install automatically on Spider as well. So once you finish GDSfactory installation, you should be able to see Spider as well. So the first exercise, we're gonna create a parametric P cell, which is a Mach Zehnder interferometer. And then we're going to route it to a gradient coupler, and we're going to show it in K-layout. So the way I usually run is I already have these two things installed. I have GDSfactory on my Python environment here. So I'm going to just delete all these. I'm going to start again from 0. So the first thing I'm going to do is like you start with basically a component. Can you guys read, or is it too small? Is the font big enough for the people in the room to see it? Let me see.
I think it's okay.
I think it's okay. Okay.
Yeah.
Okay.
Yeah, I think
So
it's right.
It's good. Okay. Yeah, basically the component is basically a canvas. So what we're gonna do in the component is we're gonna add two references to other components. So the first reference we're gonna add is gonna have an MZI. So we're gonna add a reference to another component, and then we're gonna use this GDSfactory components, which is a generic PDK that can be used for any foundry, as long as you customize it with the correct layers, because every foundry uses different layers. So the first thing we're gonna do is we added a component, which is the canvas, and then I'm gonna call it hello. Usually I don't give the components names by hand, because I usually use in the auto naming from the GDSfactory that I will show later. So this is an MCI that you can see. It has a hello is the top level component, and then it has an MCI inside. And the MCI is basically already a parametric cell that's already from the GDSfactory PDK. So an MCI by itself doesn't have too many things, but let me add a band. GF components. Let's add a band Euler, for example. And then basically this will add an MCI and a band. And if I run, it will basically put the band also on the middle, which is not where it's supposed to be. The band is supposed to be connected at the output of the MCI. So I need to do another step where I do band connect. And I'm going to put the input, which is the optical 1 port, to the MCI port O2. Then I run here, and it will show that the band goes at the output. So now it's correctly set up at the end. So this is already a component. The thing is that this component it's basically like a fixed component. It doesn't really allow you to change anything. So let's just create like a parametric cell out of it, which is basically a function. So with band, this is going to be a function that returns a component. And then I'm going to do, I don't need to do this anymore. I'm going to use some magic here. It's basically a function over a function. So this is a bit of, I didn't know the correlators in the beginning, but I end up doing a lot of things repetitively over functions. And I realized that the correlator is basically the nicest way to do that in Python. So this cell decorator, what it's going to give us is going to create a name that will automatically name this component that we are returning. So if I run this, instead of hello, we will get a good name. It will call MCI with Ben. So now the name is correct, it's MCI with Ben. And it makes it even nicer in a way that it gives you unique component names and it gives you a caching. So let's say we have a radius, one of the parameters that I want to have. The radius is, let's say it's 5 by default. And then I'm going to pass the radius to the band. Because I already know that this band has a radius parameter. If you don't know this band, you can always go to the documentation. If you hover over the thing, you can also go to the GDSfactory documentation and go through the components. And here you can see all the GDSfactory generic components. So what we're doing is we're using this band Euler. So you can read the paper where the band came from. You can also understand what every parameter means. Like, for example, in an Euler band, the percentage of the band that's Euler is called P. It has also an angle. Like most of the bands are 90 degrees, but you can do also 180 degrees. You can also define how many points per band. You want to define if you have boxes, what cross-section, like how many. The cross-section is basically relates to the layers that define that band. We are only going to change the radius in this case, and then we're going to pass. If we run it with the default radius, it will get the same name because we're not changing the radius. But let's say we want to pass a radius instead of 5, we pass 50. So you see that the radius will be much bigger than this band. We grow now; it's much bigger. Band is 50, and then the name of the return component also changed. With a unique name that basically it's every time I run, it's going to get the same name. So this is very nice. And it's going to make sure there's no name conflicts because we have this cell decorator. A component like this is a bit useless because there's no ports. We don't know how to connect to it with the outside wall. So to make it actually useful, we need to add a port. Let's say I want to port an input port called O1. That's coming from the MCI port 1, and I'm going to add a port 2 of the band O2. So now we're going to have ports. The thing is that ports are basically something that doesn't really turn into geometry. So if I run this, you won't, and I can even turn my text. So you won't see anything here. There's no port thing showing. So how do I know it has ports? One thing I can do, I can basically run it with something called show ports equal true. So this will basically add some markers at the port. and then you will know, okay, this port is going to the outside, so it's in this direction. I need to connect things. So now I can actually connect things to it. And you can even run this in interactive Python, so you actually can query this component, what are the ports, what everything. And this is what notebooks are so good to learn, because once you create a notebook, like here, you can still play with it and then change the parameters and then print and then show it again and then change another thing and show it again. The problem with notebooks is that it will only take you so far. I find it's actually, if you want to make complex circuits, it's like it's better to start with some Python IDE, like here I'm doing with VS Code. So yeah, I recommend doing both, like for knurling using maybe notebooks or maybe the browser. But if you want to start doing like big mask, I recommend that you also learn how to use an editor like this. And the thing that we can do now, because it has ports, so I can connect it to the outside wall. So let's say I want to connect it with add fiber array. I can add a fiber array to C. And this basically will return a new component. Maybe we should call it C2 because it's a new component. It will take the original component and it will add port, maybe a bit bigger. And you can see, voila, it has a grading coupler fiber array connected automatically. Let's say you don't use fiber arrays in your lab. You want to do a fiber single. So you can use, instead of routing add fiber array, you can add routing add fiber single. So you can see it add with single fiber out. You can always turn off the loop back. This is basically the reference to remove the envelope from that the grading coupler will add you. So yeah, this is like the first part of the tutorial. So yeah, if you can follow I can put this on the chat if you guys can. Okay, nice. You guys can follow along. So the idea is that, yeah, you have to do this on your end. Something you can also create is you can also create like a design of experiment where you create something like this, where you create 5 of them and then combine them into the mask. We can also do that together. So it will be very similar to this. So here in this case, we need to add another variable that will be the delta length. And let me make it 10, for example, and then the delta length should be passed to the MCI. So let's try before we run it again. Delta length. So by default is 10, but let's make something big like 100. So you will see it's a bigger MCI. Yeah, it's a bigger MCI. Let me remove also the grading coupler so we are clearly seeing what we do. So you will see it's basically an MCI with an unbalance. So and we're gonna create also like an experiment where you have 5 of them. And we can actually pack them in a component or MCI, so you can have it like this. So it will be basically, you will have a component. So they say we can do delta length equals, so let's do 5 MMIs that have 10, and then let's do 5 that have 100. And then we will make MCIs equals GF components. We can use directly the MCI, or we can use the MCI with Ben that we used before. It's up to you. Delta length for delta length. Yeah, so this will basically, it will return a few MCIs, and then we can pack them in a grid, or we can pack them as small as possible. GF pack. So if you run it with pack returns groups, so you have to send the first group. So you can actually see. So yeah, this should do it. So you can see here we have 5 MCIs that are short and 5 that are like with big delta length and small delta length. In the end, you want to connect them to the gradient coupler, so you can also add that too. So MCIs with GC equals routing for array C for C in MCIs. So you can keep increasing the complexity of your mask very fast. So you can see, you can even run it with the file watcher, as I said before. If you start making a big mask, like sometimes that second that sometimes takes to build a big mask, it's actually better just to see it live. So yeah, this is the exercise 2. We've created a parametric MCI, we routed it and then showed this is what we already finished. And now we created a design of experiments. This is usually called as a DOE. Yeah, then we also have extra examples. Yeah, I can keep going. I don't know how you guys want to do it. Like, how is the people in the room? I don't see them anymore.
There's a ton of people in the room.
There's a ton of people in the room. Okay, sure. I'll keep going, and then you can interrupt if you have questions. Does anyone have any question? I don't know how many people were able to get the MCI going. But
Joaquin, can you hear me?
oh yeah, Andre, yeah.
Okay, so the installer makes it really easy, I think. Thanks for making that. How do you actually open up the VS Code and the K layout? Because I just tried that and I ran like a simple P cell and it didn't appear on K layout right away.
Yeah, that's probably because did you also install the tools manage packages? Did you install this GDSfactory?
I installed the GDSfactory, yes.
And so when you, so the first thing you need to be able to make when you want to do a test, like let's make a new file called test. You need to be able to make sure that you can import. First, I need to make a file. There's a Python file. Demo import. So import GDSfactory at GF. So can you run this successfully and like
yes.
Because once you install GDSfactory, you have to also make sure that your terminal is using the GDSfactory that you install. So basically, if in the installation section, there's install GDSfactory. And so this basically will just like you click here, then you install, then you get the K-layout integration. So with GF, you can also do it from the commands, GF tool install, or you can do it with the GUI from K-layout. Then the second thing you need to make sure is that you have to have, if you have an installer, the easiest way is to just go open the Anaconda Navigator. Like if you go to GDSfactory, you should be able to see Spider, but the Anaconda Navigator is in a different window. But you can launch Spider, and this Spider will actually have the correct GDSfactory installed. It will be the latest one that you install. Okay, for example, this is my Simon, my colleague Simon. He's on a Windows computer, so it will be here. And then you can also run in Jupyter Lab. This is also how I make the tutorials. So these all Jupyter Labs notebooks. But on VS Code, you have to, I don't know if it's too small, you have to tell like where the base Python is, the base interpreter. So I can make this smaller, bigger.
What if you launch the VS Code from the Anaconda Navigator that comes with the GDSfactory?
That should work too. I don't have access to Windows machine, so I haven't been able to try it myself. I mostly use Linux, but yeah, the Anaconda Navigator is only on Windows, so this is what the Windows users have been doing. I think, yeah, Thomas is in the room. I think he also, most of the people in his company I think are also on Windows. Actually, I just noticed that these are exactly the same image. Okay, yeah, I need to fix this. The VS Code is basically, it will be a bit different from this. This is PyCharm. So there should be a way to choose the interpreter that you use. But is the problem that you cannot do show, or what's the problem?
Yeah, the one that you can't do show. I think that's the one. So if you could.
Yeah, try to do something like this, MCI, and then do show, and then try to run it and see if it shows in layout automatically. If it doesn't show in layout automatically after installing the macro, sometimes you have to exit layout and then enter again. You can try that too.
All right, let me try exiting. Can you show one more time how you run the script in VS Code? You just click that.
I mean, this only works if you have the Python extension. So if there is, I don't usually use VS Code, but we have the GDSfactory extension that it's basically code snippets. But there's also like a Python extension. This Python is actually done by Microsoft. I think there's actually some people from Microsoft in the audience too. I don't know if they're there, but there's some. Yeah, if you install this, you will basically, once you're in a Python environment, you will see display. But if you don't have it, you can also go to, I think, I don't know how it shows, but you will have on the samples, you basically have also like a way to run. So you can do Python demo import, so you can run from here. So if your Python is the correct Anaconda environment, so like for example, I do delta length equals 100, so I can do this. I can run it, and you will see it will show 100 unbalanced here. And something I can also do is I can also GF watch. So I can run it as I was saying before, I can run it as a live mode where you can do, as long as I save, I see it. So GF routing fiber single. So this is very fast. This is how I usually run Masco. I just save. Every time I hit file save, it will actually detect there's a change and it will refresh and I will reload it.
Mm.
So I can even go to I can go back to the mask. This is another file. I can just save it and then show the mask here. So it's pretty fast to be able to make big mask. There's also another flow that I could show is the YAML flow, yeah, for having all these nice features, it's nice that you have this Kaleo macro installed, so you can actually interact with your Kalayout directly. But yeah, once you finish, you exit, and then it doesn't watch anymore. I basically Control C, and it will abort. But we also have other things that is nice to see. So we have, like I can show you this cross section. So you can actually go to 3D images of components. This is using the 2-3D. So you can take a component and make a scene out of it, a 3D scene. So this also, it will show, this is a phase shifter, a dope phase shifter. So it shows it in layout, but because I'm also doing the 2-3D, you can also render it on 3D. And this is what we have on to be able to render on the browser, you can render in 3D. And this is something we also have on the, so if you go to the GDSfactory, we have a CMOS PDK. Or you can also see it on the GDSfactory documentation. It's part of the layers. On the layout tutorial, if you go to layers, we have this 3D rendering. So you can actually render a wake with a heater on 3D. You can see this is your metal in green. You have your vias, and this is your tiny dry heater that's above the waygate, and the waygate is here underneath. So you can, and this is basically another type of heater. So this is the metal heater that goes on top. And then here we will see the heater that basically goes where the heat flows sideways to the waygate at the same level. But this is pretty nice also that you can also do tools. If you have the GDSfactory and then if you have installed the macro, you will also see a few things. You will see the set GDSfactory shortcuts. You will see the generic, which is basically giving you the layer map for the Lucas Krostowski book. But if you have this generic layer map activated, you can do tools, 2.5D view, and you can actually see exactly the same layout you are seeing here. You can see here on the left, and I can even interact with it. So I can turn off layer 3, layer 2, layer 1. You can see them as you do it. You can see, you can zoom in and out, make sure, okay, this via is connected to the waygate. Let me turn on the middle one. Okay, the metals are connected. Yeah, you can also, if you also install these tools, manage packages, this cross section, you can actually cut the chip. This is what we can also do now programmatically for the FEM solver. So I can let me cut the chip here on the vias. So we will be able to see the vias, the tools, cross section. I can actually cut the chip and you can see the doping of the waygate, and then you can also see the vias and the metal. So this is useful to turn from a top view to a side view. You can do the 3D as well.
It's a quick question on that. Is that available in all of the different PDKs from the different foundries, or is that only some of the technology packages have that? Or
yeah, that's available on all the PDKs.
okay.
Yeah.
If you have like a custom stack, how hard is it to kind of design that for your own process?
Yeah, good question. So if you have your own process where you have different layers, and then you have a different layer stack, so you can use, there's also on that tutorial, there's also how to define your layer stack. So you basically need to get this cross-section script, and this basically will return when you will do print script, it will basically print a layout script. So this is basically a layout script that you can basically use to when you run the cross section here, tools cross section pieces, you load this script. So it depends on what you're trying to do. Like the 2.5D cross section on layout. This is 2.5D because they call it 2.5 because they don't have sidewall angles. That one, it requires one script. So you have to create this. The other one, which is the layout cross section, yeah, which with the other one, the 2.5D requires one type of script where you only have this layer minimum thickness that the layer starts, and then how thick the layer. For example, silicon, it's on layer 10, starts at 00, and it's 220 nanometers, is 0.22 microns. So if you want to do a different technology, you have to get a different script. So let's say you want to customize this one, instead of 400, it's 500. So you will run this get layer stack generic. It will give you a different script. So here you will see 10 is a 0.5 micron thick. You will copy paste this one into the tools, manage technologies, and then you will go into the generic, and then you put it here in the generic stack script. So you paste the script here. And that way, whenever you have that technology activated, when you do tools, 2.5D view, you will see it. I made a YouTube video of this if you want to be able to watch it by itself.
Joaquin,
Yep.
I have a question. This is Paolo. For the 3D view, do you have some constraint in the graphic card that you need installed? It does run more or less everywhere.
It runs everywhere. What I heard, it doesn't run on Mac OS. So, well, yeah. When I was in Spain this summer doing videos, I tried my mom Mac computer for making a video of how to install the Fresh. And on the Mac, it didn't work. And apparently I made an issue, and apparently everyone, I thought it was something because my mom has an M1, but apparently it's on every Mac. This 2.5D in layout doesn't work. So if you're on Windows and Linux, this should work.
Okay, thanks. This is pretty cool.
Something I can also show is a bit of a DRC. So I have some examples here on how to make some DRC errors, and then we can run together, see how you work with DRC errors. So the first thing, you need to create some layout that has errors. So this basically is trying to demonstrate all the errors that we have implemented on GDSfactory. So these are things that are too small in area, too close, or two layers that are too close also. You can have the same layer too close or distance between layers too close. And you can also have incorrect overlaps between layers. So you can define your layers. So this is basically, you can create your rule decks in K-layout. So this is basically, it's kind of creating a K-layout script with rules. And one of the, I think, good things of GDSfactory is that you can actually write your DRC macro directly into your K-layout folder. And you can even assign a shortcut. For example, I use Control-Shift-D for running DRC. But you can also run it from the tools DRC. But yeah, once you create this, if you run this script, basically you will write the macro directly into K-layout, and then you'll be able to do DRC, and then you can run the generic DRC, which is the generic DRC. And then it will open another thing, which is a marker data browser, which is a K-layout thing that allows you to browse through the errors. So you can see the minimum, you can read the error here. The minimum metal to heater separation is 1 micron. So here, if we use the ruler, you can see it's 0.1 micron. So it's 10 times closer than it should be. Then we have another one which this is a via. So the via should always be enclosed within metal. So it's not enclosed. So it's failing. The edges are not enclosed. Then we have another error where the minimum area it's basically too small. So these are some of the rules that you're going to encounter when you work with foundries. And then we also have a density. So this is basically make sure the density of your circuit it's between a threshold. So yeah, this is also something that you can also play with it. And everything I'm showing here, it's also all this demo. It's also on the GDSfactory GitHub repo, and then you can also access when you download. So we have samples in Python that you can run from IDE, and we also have the documentation, and these are basically the Jupyter notebooks that you can find on the tutorial. So if you git clone the repository, you can actually run all the tutorial that you can see here. You can run directly on your computer. Or if you don't even want to install it, you can also run it directly from the browser with this binder. The problem of binder is that it will time out after 10 minutes because it's a free Jupyter Notebook instance. This is actually hosted on Google Cloud. So yeah, after 10 minutes, it will die. And yeah.
Can you just open that up to show people?
Oh, yeah, sure. You basically click here, launch on binder, and it will bring a Jupyter Lab instance on basically an environment for you to play with it. You should go into the notebook section, and yeah, this is basically, you can configure, this is the Python introduction. So you can even configure your plotter. So you can plot with something called HoloViews. Bouquet is kind of like an interactive JavaScript library. You can plot edge. So you can still interact with the layout. So you can see I can zoom in and out. You can also go directly to the geometry. So yeah, this is trying to show how to manipulate geometry, how to manipulate reference, how to move. All the things that you see are also documented here. Then I can also show, so this is the tutorial. The other thing we have also made is it's a YAML flow. I don't personally use it too much, but I know people use it. So it's the kind of thing that if you don't like Python at all, you can also describe your circuits in YAML. So I could show a quick demo of how that looks. But it's basically based on electronics. It's inspired by electronics. So the way to I usually run it is GF and then watch. And then so this is GF is the GDSfactory command line. So when you type GF, you can see what you can do. You can have GDS tool or watch. So you can interface with GDS, you can interface with the tool, or you can watch things like a YAML file, for example. So I'm just gonna go watch. And then I'm gonna go to the folder where we have some YAML flow. The YAML flow is kind of like, it's very compact because basically it's a place and outer route. So here I'm placing 4 paths. So I call them bottom left, top left, bottom right, top right. I define the X and Y of the path, and I define the routes. And I route 2 of them, I route them with metal 2, and 1 of them I routed with an optical route, which is gonna be in layer 1. But I need to do the same as before. I need to change this and then save. So every time I make a change and then I hit File, Save, it will show it directly on KLayout. And then if I do, I can see what my circuit looks like here. And this is almost like it's a code-driven flow, but I can move things almost like in a GUI like, so I can move this path up or down. I can move up, I can move down. And then it's still routing to the other paths. So you can also change the route parameter. So here I'm doing like 10 micron routes, but I can also make them like 1 micron. So you just save and then automatically changes the route. And we have also an optical route that has like 100 micron band radius, but I can put it to 10. I can just cut it by 10 and then it makes a more compact layout. You can also take this with, so you can define your pixels like this too. Like this is just an MCI from the UBC PDK. The UBC PDK is the one that Lucas Krostowski uses on his course. So you can define like a parametric cell that has 2 splitters and then 2 routes. And then I can define what's the delta Y of the bottom route. So here it's minus 300, but I can make it 100. So now it's 100. So it's basically you define some settings, and then you can use the settings also on your component. We use this dollar sign, and then the name of the variable, and then the settings dot the name of the variable. And then you can take this into, like, let's say you want to do a lattice filter, where you have 2 MCIs rendered with 2 grain couplers. So it's a place and route, so it's very easy to define placement of one component relatively to another. So here I'm doing the MCI2, the Y max, it's at the MCI north, and then I have a DY over 100 down. But let me just put them at the same level. So this will basically, it label them up. So I can change the settings and the placements. Let me just make them a bit shorter. Let me say, let's just do 20, 110. Let's make it much smaller so you can actually see. You can see 10 didn't work, so you get a routing error. It's labeled here. I cannot make the DY 10 because I need to have 2 bands that are 10 micron by default. So I need to make them 20 at least. So this is kind of like you define your instances, settings, you define your placements. Like I'm gonna define the placement of this grading coupler 1. Let's move it up. Let's move it at 0, 0. So you move it right away. So you can see how I get kind of like a GUI-like experience, but at the same time it's code. So I can actually put this into a for loop. I can do many different things. And then I can save it, store it, and it's easy to reproduce and easy to control in Git. And I can even do a mask, for example. And here I'm just a bunch of rings and a bunch of MCIs. So you can see, you can run it like, you can do both. So it's a file watcher. So you can open this, pick your YAML that can look for it. or I can go to any, like, yeah, you can launch it wherever you want. It will just look the files. It will observe a particular folder. It will register all the PKO YAML as P cells, and it will watch anything that you change. Like, for example, this is the MCIs that we were doing before. So I usually do my mask like this. It's pure Python, but there's some people who really like the YAML. So yeah. And yeah, and the last thing I want to cover is the connectivity checks. I think that would be kind of like a good overview of everything that we can do. So connectivity checks is basically a way for you to define when things are connected. So if you start making complicated layouts, you're gonna be able. Sometimes you can also make errors. So these connectivity checks will make sure there is no opens or shorts. So the way to run connectivity check is you use this netlist trace. So trace nets. So you can trace the nets hierarchically. And here I'm path with routes. This is the name of the. So here I have two nets, the top net and the bottom net. So a net is basically something that starts in one component and something that ends in another component. So there's two nets. But let's say by mistake, I add a box on metal 3 that's basically a short. So if I go tools, netlist tracer, hierarchical. So if I go path with routes, now there's only one net because everything is connected. So that's basically an indicative of you have something wrong. So this is also something that we're currently adding also, so you can actually do it programmatically. And yeah, like yeah, I could keep going about like all the workshop things, but the best thing I recommend you is to go through the tutorial and then yeah. So notice that some of the tools will work only on like Linux, like for example Meep. But yeah, Sax now works on Windows too. But yeah, like most of the things you should be able to do in any computer. And does anyone have any questions?
Yeah, let's start Q&A. I bet a lot of questions.
Yeah, I have one. Can you hear me?
Yeah.
Okay, so it's about the DRC. You said that there was a density violation. Is there a dummy fill operator built in GDSfactory?
Yeah, so GDSfactory has a, if you go to GDSfactory, I think we have a field. So basically we have you can create a component, like let me run this, you will see. It's basically, you create a component, you define which layers you want to fill and what densities you want. And then if you go to layout, you will see it here. Here I'm not making, I'm filling everything, but I'm not avoiding the layer 1. So you can see it fills even around. But let's say I want to avoid layer 1, so I run this. You will see it will avoid that specific layer. Yeah, it will avoid the specific layer that I'm trying to avoid. But then you can also use layout. So layout has also a fill tool. So if you go to edit, so utilities, fill tool. So you can actually programmatically from layout define your fill as well. You have two options.
Cool, thank you.
I love a question. You know, there are a lot of APIs connecting to different simulation tools, like thermal simulation, mode simulation, all that kind of stuff. Those are really cool. How do they compare to the commercial tools?
Yeah, like I have benchmarked, like the thing with commercial tools, like some of them have on their contracts, they have something saying that you cannot really benchmark, but we have benchmarked all these tools as commercial tools. So if you look at the TICA simulations that are on basically the documentation have also the TCAD simulations. So this basically match exactly the example from the numerical website on numerical device. On the thermal one is something that we recently do it. So this one we haven't benchmarked yet. But in terms of FTD, I've been benchmark FTD from numerical and MIP, and yeah, they're equivalent in terms of speed and accuracy. The only one I found faster than MIP and numerical is basically this TiD3D. So TiD3D is a proprietary commercial software. It's a startup from Stanford. So they have this GPU-based FTD. And I found this one, this is actually orders of magnitude faster than both numerical and MIP. So in numerical and MIP, gradient coupler 3D simulation can take 45 minutes. Here it takes 45 seconds. But you have to submit the jobs to their cluster, it's a GPU cluster, and you have to buy credits for you to be able to run FTD there. So every 3D gradient coupler can take you like $40 to $80. Most of the simulation take around $2. I mean, depends on how big the simulation is, but it's pretty fast.
How about in terms of accuracy? Accuracy probably no problem, huh? Like the modes.
Yeah, it's basically highly parallel.
Yeah.
So they code it into GPU. So yeah, it's accurate. You have to also make sure that you're like here. The samples I show, the mesh is kind of big because I want them to run fast for the demos. But yeah, when I usually run, I run with higher mesh accuracy, and yeah, you can see here it's a bit rough the mode simulations.
Wouldn't that be disrupting to some of the businesses out there?
I mean, photonics is growing like crazy. So there's going to be more startups coming into this computational electromagnetics market. So I think the pie is big enough for small startup, big companies, and open source alternatives. I think if I were a student, I mean, now even though I'm in a company and I have access to all these commercial tools, I try not to use them if I can, because as I said before, it's easier to scale up to thousands of simulations, and I don't have to worry about license servers. I can run on my laptop, even being offline. So when I started my PhD, I basically use only commercial tools because I didn't know there were open source alternatives. But now I think for the people who are at school or starting their careers or even far in their careers, I think it's pretty good that there's open source alternatives that match or even exceed the performance of commercial proprietary tools. So you can actually understand what you're doing. You can share it with your colleagues without them needing a license. And if you also be a part of a small startup, most of the times you won't be able to afford these proprietary tools. So having an open source alternative for small startups is also very important as you scale up. Also, you don't need to buy more licenses. It basically removes a lot of headaches on your design workflow. And that's what in the end I've been moving away into all open source tools. And I've been using all open source tools for the last 3 years that I completely fully open source. And that's also what I'm trying also to get more people into it, because the more people working on these tools, the tools will be better. Yeah, I think and as I say, the pie is big enough for everyone. Like it's the same like Linux. Most of the internet runs on Linux, but yeah, like Microsoft and Apple still have a big piece of the market because macOS looks beautiful and Windows is very easy to use. So there's going to be always some market for these proprietary tools where you can actually call someone if you need something if it doesn't work. Like in this open source tool, you have to create an issue. You have to you can. The good thing of this is that you can also fix them yourself. So it has a good thing and a bad thing. The bad thing is that if it's only you, who wants a feature and don't know how to do it, then you probably cannot do it. But I'm pretty sure also in commercial tools, like if you're a part of a small company or a university, they won't listen to you either. So
yeah. Stefan, do we have other questions from the audience?
So the geometry for the simulation tools, is that generated from the GDS file?
It depends on the tool. Like for example, like some tools we automatically create the mesh directly from the polygons. Most times we save through GDS, which is kind of like the PDF of electronic circuits and photonic circuits. So it depends on the tool. Like for example, on Tidy 3D or numerical, we save to GDS and then we load on the back. You don't even see what's happening, but you basically create a component, use the GDSfactory simulation.numerical FTD, and then under the hood it will save the GDS. It will import it in numerical API or MIP. That's the same thing. Yeah. So some of them we don't need to save to GDS, but yeah, depends on the tool.
In those cases, is it possible to generate like trapezoidal waveguides, for example?
Yeah. We support like sidewall angles, erosion, dilation. So it also depends on the tool. You can see here I'm doing a 45-degree sidewall angle, trapezoidal waveguide. You can also do erosion and dilation. So this is something that it would be nice to also have. I think actually the sidewall angle is something that Thomas Dort also implemented. He's there. I think we have both that in. I don't think we have it in MIP, or maybe we do have. I think we have it in MIP. So Thomas did the MPB and MIP, but I've lately been using the mode solver from Tidy 3D. So Tidy 3D, their mode solver is open source. The FTD code is not open source. So this is actually a good example of a hybrid, proprietary and commercial, proprietary and open source. I don't like to say commercial because you can, like for example, Red Hat is commercial, but it's open source. So you can be open source and still make money. The mode solver of Tidy 3D is open source because it runs on the client side. Their FTD, because it runs on their GPU server, the GPU cluster, that's not open source and the code is not available. But for the mode solver, they also have sidewall angles too. This is the one I've been using recently.
Wow, this is really a lot. So everything you're presenting, including the slides, are available on the website, right?
Yeah, if you go to the website,
okay.
It's basically slides here.
Okay, great. So we don't have fear of missing out.
Yep.
Any last minute question? I think we're already like 15 minutes time.
Really quickly, I saw that you could do a signal transistor simulation, like process simulation, but is it also possible to do electrical circuits?
Yes. Yeah, we can. So I mean, we can do electrical simulations as part of the device simulator. So we have TCAD. So TCAD we can compute what's the and we have coupled these with the Tidy 3D open source mode solver, where you can compute the mode overlap with the electrons and holes. So you can compute the refractive index change of your waveguide as you apply different voltage. And there's also other device simulation that we can do. And this will be kind of like what I'm showing here. This is basically, so you can do NMOS, PMOS transistor simulations also. We haven't, I mean, I'm a photonics engineer, so I'm not doing like transistor level simulations, but we've been working with some open source developers at Google trying to make this flow also available for CMOS. So it's part of the Skywater open source PDK that is also available on the GDSfactory organization. So we basically have a technology that basically it describes the process of the CMOS. It's not. So you have P cells also similar to what the P cells I show, and you have also standard cell libraries. So you can use the same flow to layout. You can also render the circuit in 3D. So you can lay out and simulate also CMOS chips. so this week there was also asking someone in the forum if we can do digital design. I think it would be really cool if we can do it. I just don't have the time to look into this unless I need it. And so I mostly develop the features I need, and I'm sure all the other developers do the same. It just for us it doesn't take too much effort to share because it's basically a foundry agnostic workflow. So we all benefit from improving the tools. And yeah, like the next thing we need to add to make this flow available is to add PySpice. So this is something we've been playing with to support different SPI simulation.
Oh, that's great.
Yeah.
Well, I guess, Joaquin, we should wrap up. It's we're running out of time, and I don't want to keep people, occupied as well as you occupy. And this has been really wonderful seminar and workshop. And just so everybody knows, this is recorded, and we'll put the recorded video on the website. We'll probably send out an email of this recorded workshop, as well as more information for your website and docs and slides. So we don't have to worry about missing out. And thank you again, Joaquin, to do this seminar. This is really wonderful, and it's eye-opening as well. And thank you all for attending.
Thank you. Thank you for attending.
All right. See you guys.
Bye.
Thank you.
Thanks, Joaquin. Thanks. All right. Bye-bye.
Thank you, Dee. Thank you.
All right. Bye-bye.